Five, four, three, two. Hello, everyone. The interaction, exchanges, and movements of large numbers of pedestrians lead to complex and beautiful movement patterns that have fascinated historians and sociologists for ages, for decades, for quite a while, actually. Crowds throughout the years have often been seen as a collection of single individuals who adopt the behavior of the whole entity. Basically, everyone, masses of people will lose their own identity following the general trend of what people are doing within the crowd. There's lots of stories of people in the crowd losing their mind and just following the crowd itself. For instance, the storming of the Bastille is just seen as lots of crowds, all individual, lost, all together storming it. However, though, nowadays modern crowd studies have gradually shifted from looking at the crowd as a whole to more like a crowd with an individualistic term, with group behavior, as pedestrians are more likely to walk as groups, in small groups, and they have social ties with other people, and they change their behavior in a crowd setting according to other group members. Crowd scientists are using the recent advances in computer performances to simulate large environments crowded with countless pedestrians in real time. However, though, the goal of building a realistic crowd simulation, one that is as truly as realistic as possible, is still a very, very distant aim. There's still plenty of problems that need to be solved in rendering, generating animation, behavior, etc., etc., etc. So hello everyone, my name is Szymanezyk Olivier, and throughout this talk, I will introduce some fundamental changes and concepts of crowd simulation technologies, and I will often dip into psychology, video game development, and hopefully share with you my passion for the simulation of crowds with a focus on AI. So again, for the next 15 minutes, I will talk about crowd simulation, crowd research, problems with crowd simulation, solutions with crowd simulation. I will talk about games technologies and give some insight about crowd movement. So yeah, again, my background is in I'm doing game dev stuff at the School of Computer Science. I am a lecturer in computer science with focus on games at the School of Computer Science. I've got a background in crowd simulation, a background in crowd AI. I've also done quite a lot of stuff on indoor mapping system, indoor location system, etc., etc., etc. By the way, if you've got any questions or would like to say something or just give some feedback, don't be afraid to use the chat. And I've got Kieran who will pop some questions as well. If I can't answer them throughout the lecture, I will answer them at the end. So don't be afraid to put feedback, comments, anything in the chat. Also, feel free to send me an email. And also, if you're a student from the University of Lincoln and like to access those slides, they will be available on our Blackboard quite easily. I can send them to you. That's not a problem. All right, introduction. We're currently living in unprecedented times, and despite the ongoing situation with COVID, there are countless crowd gatherings happening throughout 2020 and 2021. Well, I'm not going to go over the example. There's a couple of pictures of a recent event, crowded event from last year, over summer, last year in Bristol, last year, actually that was this year in London. I also had a picture of the Lincoln Christmas market that started the lecture, and that was attended over 4 days by 276,000 people. That's a lot, yeah. As we resume our everyday life post COVID, large crowds are expected everywhere at public infrastructures such as shopping, commuting, traveling, and there will be even larger crowds expected when people are starting queuing to get their booster jab. Actually, I was talking with Kieran, who is hosting this, basically another lecture about queuing and going to get the booster jab. Okay, that's a different topic. Anyway, what's happening now is those shopping areas, those commuting areas, traveling area, booster jab areas, they're bracing themselves for what will be most likely the busiest days ahead, especially with Christmas coming up. However, even with a vaccine and the situation getting better, and even with booster jabs, the The lockdown has changed the habits, has changed our habits. Safety is first and foremost on our minds, and keeping crowd movement and crowd safe, sorry, is top of the mind for the government, for companies, for universities, etc., etc. And also, research shows that physical distance is critical to ensure the safety of communities. People physically separating themselves from others help to stop the spread of the virus. However, there's still a need to accurately monitor the movement of people and to find ways and insights to plan, assess risk, and implement measure. What we need are cutting edge tools based on science to accelerate and inform decision making. So, what we need to make sure that crowds are safe are crowd simulation tools. So, tools where we can create an entire environment, simulate a crowd going through it, and find out what is the best way to stop the spread of the virus to make sure that crowds are safe. But not only to stop the spread of the virus, to make sure if an event is happening at that particular location, that people can find their way around, that they can ingress out of the area into the area safely. So what we need is crowd simulation tool to create the data, to get the data, and to find ways to navigate the new normal that is ahead of us. However, crowd simulation is not a new field. It has been around for about 30 years. It has been around in architecture, for instance, to find out the egress times of a building, to find out if a staircase has been put correctly or designed correctly, to find out if fire evacuation drills are going as expected. However, though, with recent advances in computer performances, we can simulate crowd environment in real time. Because, for instance, in architecture, couple of years ago, but 20 years ago, it was just a statistic, basically just a curve to find out if it works enough, if the results are good enough. Whereas nowadays you can simulate in real time. You can just spawn thousands of individuals and see on screen if those individuals find their way around. However, though, there's still plenty, endless challenges, as I mentioned earlier. However, though, let's jump into a different field. We've got video games, on the other hand. Video games development has done endless progress in numerous fields over the last couple of years. Can we learn something from video game development and video games techniques, video games technologies that we could perhaps take over into crowd simulation? Because if we're looking at old games, I've got a couple of screenshots on the screen. It shows that simulated crowds have played a major part of a lot of games over the last few decades. For instance, we've got the cheering crowd in FIFA 98. We've got the enjoyments of thousands of individuals in theme park construction games like Theme Park. And we've got the management of crowds in SimCity. And we've got even a screenshot from Hitman with thousands of people inside a nightclub, inside a nightclub, sorry, not disco. And basically, the high and lows of simulated crowds have fascinated players and game designers alike. However, in old video games, crowds were quite simple. For instance, in FIFA 98, crowds were simply a 2D static texture where crowds were jumping up, jumping down, jumping up. That's it. And in modern games, okay, that's SimCity. It's still a bit old nowadays, but still works. It shows crowds simulated as statistics. So, for instance, if there's a statistic that the area looks busy, it just creates endless individuals there, simple as that. And the individuals don't look realistic, it just makes the area look busy. Good enough. However, though, since the release of SimCity, there has been major advances in computational performances. Video games developers are want to create larger, more believable game worlds with endless game assets. Game designers are also introducing virtual crowds to make those virtual game worlds feel more believable and more alive. Because having more crowds, a lot of people say it increases the fun factor. Crowds do make video game worlds feel alive and makes games feel quite fun. So let's add more crowds. There's another example that I do like about crowds. There's a screenshot from a popular first-person shooter, a popular mission that relies heavily on scripted events. In this mission entitled No Russian, the player was required to interact with a simulated crowd in an airport as part of a terrorist attack. The objective of the mission was to cause as much distress and havoc as possible. And the virtual crowd simulated can be seen, for instance, to surrender, to help each other, and to run away from the player. And in my opinion, that was simulated in a real, believable way. That was really good. Also, there's modern video games. For instance, that's a screenshot from a tech demo that was released last week. And it also shows a city in the Unreal Engine that has been populated with thousands of individuals to simulate an entire city with thousands of cars, thousands of individuals walking around, etc., etc., etc. However, though, as I mentioned, simulating crowds as part of a 3D world is still a very challenging task. Even though I showed you a couple of good examples, there's still no off-the-shelf solution at all. There's a lot of progress in pedestrian dynamics and crowd simulation that still require additional research. Because if we take a crowd and we want to simulate it within a video game or any environment, we've got to think about rendering, we've got to think about generating behavior, verification and validation. Rendering, how can we render all those characters on screen? Generating, how can we render thousands of individuals that each look differently? Because you look at a real crowd, everyone looks different. You don't have clones of each other. Perhaps you see the same people wearing the same jumper, but you won't see that same person 10,000 times. And then the next problem is behavior, AI. How do we get all those individuals within the crowd to behave realistically? And of course, verification and validation, that is important. How do we know that the simulated crowd is realistic? How do we know whatever is on screen is as realistic as possible? And very often in a lot of crowd simulation, there's a trade-off between the complexity of each individual and the size of the crowd. You can have a massive crowd that looks and behaves realistically, but in the end, similar to what Charles Fox says in Guitar Hero, it's just a handful of individuals at the front that look and feel realistic, and then the rows behind them are just copy paste of the first row, so slightly shifted to the left, slightly shifted to the right, with a different hue to make it feel as if it's different individuals, but it's not the case. So it's a massive trade-off. So yeah, Charles, thank you very much. Charles in the chat, thank you very much. Guitar Hero is all about the crowd response and playing around with the crowds. So this talk, I'm going to focus on AI and verification and validation. Otherwise, I'll be talking for the rest of the afternoon / the rest of the year about all the other crowd stuff. For behavior, interesting, we can dip into psychology and we can dip into video games technology. For verification and validation, we can go into automated video analysis from imaging. We can also look at robotics and AI solutions. So yeah, Vasper in the chat says, reminds me of the Matrix where the crowd is copy-paste. Yes, and that is done on purpose to give the idea to the viewer that they're actually watching a simulation. It feels believable, but in the end, they're leaving enough hints to make the crowd look slightly wrong, slightly not correct, to ensure that the viewer understands it's a simulation. Vasper, that's a very good comment. Thank you. So I'm going to talk about behavior and AI first. I've got here a picture that I took a couple of years ago of the crowds in the high streets of Lincoln. Yes, it's already a couple of years old, because for the viewers who are watching this from Lincoln, they know that nowadays this building is gone and there's a bridge above it. But even with a bridge, whenever the rail line is down and a train is about to go through, you still see a lot of individuals just queuing on both sides of the train line until the train line goes up and people start walking from left to right. They avoid the bridge, not sure why, because actually it's got a nice bridge anyway. And what happens there is a typical example of crowd behavior, because people don't really know how to behave in a crowded environment. So what they do subconsciously, they just follow the person in front of them, who also follows the front of them, who also follows the front of them. And what happens then is something that looks a bit like this from a top-down perspective, that you get flow of crowds, that you get like lanes that emerge just because of people following the person in front of them. And you can see that behavior quite nicely now, especially with the bridge being built, that you can go into Lincoln High Street, wait for a train to come, go on the bridge, watch down, wait for the train to go past, And then hopefully don't wait any longer, and you can see those lanes of crowds being generated. It's absolutely fascinating. And that is a typical behavior of crowds, quite simple, and it works. And there's a model to express that behavior in maths. And that equation is called the Helbing social force model. The Helbing social force model has roots in psychology. It has been around for about 20 years. However, though, when the guy created it, it was just a theory and nobody implemented it as a crowd simulation. However, though, over time, people took that theory and implemented that maths as part of a crowd simulation. And to explain to you the maths, oh, I'll do that in a second, sorry. The idea is Helbing social force model is basically just calculating a force that you take an individual and you apply some kind of force on it. And the force of the behavior of people in a crowd is the sum of several forces that correspond to things that affect the behavior of individuals. Stuff like, I want to go next to this stall at the Christmas market, or I want to go to this shop, or I want to go to this location, so I'm attracted to this place. And at the same time, I want to avoid the crowd that is left to the right. Oh, I see a friend, I want to go close to the friend first, then move to the shop, etc., etc., etc. So it's like summing all the forces together and then apply it on a person. And bizarrely, those simple rules are enough to create emergent behavior. As an example, well, I can explain the maths to you. There it is, as simple as that, and then switch to the next slide. But to make it a bit easier, I'm gonna draw it on paper. So please bear with me while I move the camera around, because I think explaining stuff on paper is much, much easier. And thank you, Karen, for putting me on full screen. And I've tested it earlier, and it works quite easily-ish. But of course, whenever I do something live, it takes ages to set up. That is fantastic. Yes, I can see on the screen. People can see my piece of paper. That is brilliant. So let's go back to my example that I'm drawing top down, by the way. I'm this particular individual represented as blue dot, and I want to go to this shop here. So in terms of vectors, it's quite simple. I do have a vector that points towards this direction. That's great. But let's assume I've got here in the middle somebody who distributes flyers, and I want to avoid that person. So the idea is, using Helbing social force model, that this person creates a vector towards me, and I can normalize that vector as well. And I'm adding, perhaps perpendicular, that vector to the direction that I'm moving. So in other words, this vector, adding it perpendicular to here, and then I'm summing those two together. So basically the vector where I want to go to, plus this that I want to avoid, and that generates this new vector. So actually, instead of going forward, I will go towards the side and avoid that particular individual. That's great, but let's assume as well, I am also trying to avoid, there's a wall here. Adding more and more stuff. And this wall, I can calculate the normal out of it. The normal would be something like that. And what I can do is also add this normal onto the vector that I'm currently calculating. So it would be, in addition to this, like this. So basically this vector added on top, and the resulting would be a vector that avoids mostly the wall and still avoids this. That's great, it works. What I can do as well is perhaps add more weight to it. So in other words, I can say this vector, wall, it's more important to avoid the wall than avoiding the busker. So I can even add a weight on top of it, basically saying wall, I want to avoid it 8 times more than avoiding the busker. So therefore, this vector to avoid it will be slightly stronger. Actually, 8 times stronger. So therefore, perhaps my resulting result will be going there. Then I do that at every step. And at the end, I will get something along these lines to go to the shop. That's just a little example. May seem like a lot, but just shows by just adding vectors together, I can create very simple and bizarrely realistic human behavior. Moving the camera back. And if Karen can switch my slides back, that'd be fantastic. Basically, the slides as full screen, please. Thank you very much. So yeah, in 1999, Halbing created that algorithm. And it basically just says, again, person wants to go to a direction, calculate all repulsive effect, calculate all the repulsive interactions from other individual, and the attraction forces, etc., etc. And that would be the math behind it. Just basically just look at all the repulsive effect, other individuals, and all other attractive forces. And he implemented it. Actually, not him, somebody else implemented it. And that is one of the first implementation of the Helbing social force model in a simulation. I see there's a question from Vesper. How would you determine which way the perpendicular vector goes? That is indeed a very, very good question. And there is papers about cultures, about avoiding people either to the left or to the right. And the way that I implemented it is always to the right. However, I remember on the continent, southern countries, it's mostly to the left. So basically, it depends which culture that you want to simulate it in. Anyway, here I've got, I hope that answered the question. Meanwhile, on the screen, I do have a video of Helbing social force model. It works. It's quite simple, but it works. The results are there. Again, behavior in Helbing social force model is simulated as a physical force, and it works brilliantly. So in other words, we're taking each individual and we're calculating the force of each individual and applying it at every frame. And there's something that does that incredibly well, basically calculating forces, applied on individuals. And first-year students in games computing at the University of Lincoln are using that is applying force in Unity, for instance, or applying force in physics for third-year students, or applying force in their own force model for second-year games computing students. Basically, there's games technologies available to do all that physics stuff. Because if we're looking at games technologies, we've got middleware physics engines. Middleware physics engines are literally libraries of code that already do all the maths behind it, all the maths for physics, all the maths for calculating forces. And we've got things like that you've probably seen before whenever you start a video game, like logos like Havoc that pop up, logos like DMM, or logos like NVIDIA Physics, which I still can't pronounce properly. And they do, it's basically, as I said, a library that does all the maths of everything. All the maths, not of everything, of all the physics. And they work, they're brilliant, they're multi-platform, they've got excellent performance, they do all the physics. So why not use that? Because again, those middleware engines have been used in endless games. I've got here No Man's Sky. I've got here Stunts, which created their own physics systems. That was back then in the 90s. Screenshot of Trespasser, fantastic game. One of the very first game with a proper 3D physics engine, and the entire game was about moving things around and in physically correct worlds. And of course, screenshot of one of my favorite fighting games on the Switch, which name is eluding my mind. Of course, Super Smash Bros. Marvelous. Super Smash Bros. Yeah. Can't pronounce. Fail English, Oliver. Happens. If you want to help me in the chat, go for it. Super Smash Bros. Melee. There we go. Thank you. Patting my own shoulder here. Anyway, again, those technologies exist. And I was thinking back then when I was doing my PhD, why not use those game technologies to do all the crowd simulation stuff? However, though, one of the big problems that people come across, especially whenever they start coding more complex stuff, is the big O notation. What is the big O notation? It is used to classify an algorithm according to how the requirements grow as the input size grows. It describes the performance or complexity of the algorithm. In other words, if you've got an algorithm that's got loads of operations and lots of elements, and the algorithm is categorized somewhere here, that's actually quite a bad complexity. In other words, it will take ages to calculate everything. However, though, if you've got a complex algorithm with, let's say, something around here, that's good because the complexity would be fair. Actually, what we want whenever we write algorithms is to have excellent algorithm with a O1 that is frankly impossible to create. Well, not impossible to create. It's possible to create, but it would be fantastic to have an algorithm that goes through everything at instant time. But to explain this better, the big O notation, I'm going to do more drawings. So I'm going to move my camera again. Thank you, Kieran. Because I'm going to show a little example about crowd simulation where the big O notation is important. Because if we've got an individual here, and in my crowd simulation, I've got other individual as well. So if I want to calculate the repulsive force towards all those individuals, so what I would have to do is take me, and then I have to go through each individual that there is. So I have to go to this individual, calculate the vector, then to this individual, calculate the vector, then to this individual, calculate the vector, this individual, calculate this individual, calculate the vector. So that's already 1, 2, 3, 4, 5 operations. That's great. So I've got 5 operations. But of course, I want those individual, everyone else to behave as realistically as possible. So of course, I've got to do the same thing for all other individuals. So I've got 1, so I need to do calculation from here to there, calculation from there to there, calculation from there to there, from there to there, from there to there. That's another 5, etc., etc., etc. So you see, by just having 1, 2, 3, 4, 6 individuals, I need to do quite a lot of calculations. Actually, people who were watching this chat, this talk could even say how many individuals I need, how many operations I need to do. Because in terms of code, I would have to go for 1 individuals to all others. So basically n minus 1, because I'm not calculating myself. Then I need to do another for loop, so a for loop within a for loop, etc., etc. Basically, a lot of calculations. And that is bad for the big O notation. Because I've only done here quick calculations for 6 individuals. But imagine if you're doing all those calculations for, let's suppose, 10,000 individuals. That's a bit silly. So yeah, Vesper, thank you very much. That's exactly the number. That's correct. Yep. And yeah, if I've got 10,000 individuals, it would be 10,000 minus 1 to the power of 2 calculations that I would need to do at every frame. Yeah, the engine wouldn't. Yeah, the game engine wouldn't be happy with that unless you've got a performant computer. You don't want that. So the idea is, let's find ways to put the intelligence about crowds that we want to do, not in the data, but in the code. And of course, in games computing, in games programming, there's already solutions for this that has been programmed. For instance, we've got spatial partitioning. In other words, spatial partitioning is taking a game world and dividing it into a grid, into cells of equal size that are overlaid on top of the world. And that is a standard technique that has been used in endless video games. And you can use that basically also not only to store information for the AI, but also to say, hey, this particular cell is a little plant. This particular cell is a path that can walk. And you can add more layers on top of that. You can even say, hey, this particular cell is a footpath. And on top of it, you can walk on it, and walking is quicker, or cycling is quicker on it than cycling on grass. Fantastic. So the idea is to create the game world into a 2D array and have loads of 2D array and basically have different types of information layered on top of each other. And that technique is common, used in a lot of video games. Here we've got a screenshot of the development mode of Company of Heroes. It does exactly the same. It divides the world into cells, into grids of equal size, and then it says, hey, this particular grid, individuals cannot walk into it, etc., etc. Interestingly as well, this world is dynamic and can change. So for instance, if you destroy the wall within the game, it also changes the information on the grid. Therefore, individuals can walk into it. Brilliant. And that works fantastically. People don't always notice when playing the game that they're playing as part of a grid. If we go back to Pokemon, it's quite common to see that you're pressing left, it moves from one cell to another. But in the end, does it matter? Not really, because the game world still feels alive, still feels good, and it's a good way to spread the information in the world and not in the data. And again, a typical picture, they've got different layers. For instance, one layer, it says all the solid walls. The other layer, you've got an individual sitting here, and that individual can see those cells. And if you overlay on top of each other, you can find out this individual at this particular area can see this wall. And of course, I can't have an example without Pokemon, without Snivis, without Charmander. So I've got different layers, a physical layer, an agent layer, and I've got, let's suppose, a wall in cell 4, 5, 4, 5, 5. They're all set as walls in physical layer. In other words, a person cannot walk through it. Then we've got the agent layer that says that keeps track of the position of every Snivis and every Charmander in the world. So I've got 5, 6. And would be here. I've got my Charmander. I've got in 2, S1 my first Snivy. In 4, 3, I've got Snivy 2. I've got another Snivy, etc., etc., etc. So what I can do is use this world and query using Charmander what is around that particular Charmander. Basically, by looking at the more neighborhood of depth of 1. And what I can do is find out, oh, this particular Charmander, what can they see? They can only see a wall at position 5, 5. That's great. And I can repeat that approach for other agents as well, for other characters within the game world. For instance, S1, Snivy 1, checks the neighbors. They've got no neighbors directly adjacent. I can repeat that for each agent, etc., etc., etc. Let's have a more complex example. I'd like to find out what the neighbors are of this particular Charmander. I move the Snivies around. So I'm doing the same thing. I've got my grid world, and then I'm using Charmander, and I say, Charmander, find the neighbors of that particular world. And the world will just say, hey, I've got S3 in position 6, 5. I've got S2 in position 5, 7. Great. And that's actually really good and really quick to access, because I don't have to query everyone within the world at each frame. I just query the world. Hey, I'm on this particular cell. What are my neighbors? Of course, I also got another neighbor, which I forgot to mention, which is the wall itself. Of course, if you've got different layers, you can also query not only the layers of other individual, but also the layers of all the walls, of all other enemies, etc., etc. And that's the power of spatial databases in a nutshell. Another example, again, with Snivy on S3. Snivy would like to know the neighbors according to more neighborhood, -1, +1. Got a wall here, a wall here, and a Charmander here. Fantastic. We're not limited to the size of the cell to one individual. For instance, here I'm always putting one individual per cell. We can set the cell to a size that we want. However, though, at the same time, we're losing some information, because the bigger the cell, the less detailed the world becomes. For instance, this example, we've got here a Charmander in cell 3, 3. Queries, what are my neighbors? It will say there's a wall in 2, 2. And in 3, 3, there's a Snivy and another Snivy. So it works. There's a good question by Charles Fox. Are you using spatial databases as in GS tools? I haven't applied this on GIS tools using PostGIS. However, though, I'm aware of specific companies that are working in Lincoln, for instance, Eventis, which are doing that. And I remember talking to them about spatial databases for simulating crowds at events, and they thought it's a good way to basically make sure that the algorithm works. So there's methods to do that. However, though, I haven't used it, as Charles said, for GIS tools. What I did is I created my own crowd simulation from scratch in C++. I wrote my own game engine. I used GLOT, OpenGL. I used PhysX 2.8.4, yes, an old version now. And I used an airport terminal to simulate the behavior of individual. And I put that video online. And that's actually the crowd simulation that I created. It's quite an old video by nowadays standards. And what I did not focus on graphics. I'm using simple Minecraft-ish characters, because Minecraft-ish characters are actually quite good to model, quite easy. They're low polygon too, but I mostly focus on the AI behavior. So I've got here the top-down view. I've got individuals coming in. Since it's an airport, individual have to go to check-in counters. They've got to avoid other people. Sometimes they want to go to restaurants. So we've got plenty of individuals queuing, walking, avoiding each other, and then I'm making it as busy as possible. I'm exaggerating on the business, so people start pushing each other because some of them may miss their plane, so they're pushing other people out of their way because as they're getting a bit more aggressive. I wanted to make it a bit more gamey. And what I'm doing here is using a spatial database. Yes, the entire world is divided into cells, and an individual, whenever it wants to know what's happening around me, instead of calculating the helping social force model with everyone, it just queries the world. What are my neighbors? Can I calculate something with only my neighbors instead of checking the entire world? And it works. It works brilliantly. I just noticed you can't really press forward and backwards to shift the video. Yeah, example of the different layers. I've got the paths pre-calculated to go from each cell to each cell. I've got information about the occupancy layers, so individuals will try to avoid cells that are busy in front of them. Also, each individual has got a field view, so they know which cell are in front of them, which cell are around them. And it works brilliantly. It works brilliantly. I managed to create, 6,000 individuals, and I had over 30 frames per second. And individuals found their way around, even if they crashed into each other. Yeah, and I was using games technologies to simulate that, and it was fantastic. However, though, people who watch the video, everyone watched the video. People with a keen eye on the video noticed that in my simulation, I'm simulating individual on their own. And that is a problem in helping social force model. It does not take into consideration people that you're part of a social group with. Because nowadays, people have got social ties with other people within a crowd. To walk next to each other because they're friends or perhaps it's family. And the coordination, communication within those groups heavily impact on the flow of crowds. So it's great that we can simulate crowds, but we want also to simulate groups of people. Because there's been quite a lot of research done using, for instance, evacuation system, using the helping social force model only. And you can see on the simulation people standing up and then walking towards the corridor and then leaving the building quietly. But that's not the case in a real life situation when there's a fire alarm, that people stand up, they look around, then they walk to their friends or colleagues, and then they walk out as part of a group. And that affects the behavior of the crowd a lot. Because again, people want to communicate with each other, etc., etc. And that would be a standard example, for instance, of a crowd with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 individuals. That you've got individuals who are considering themselves as part of group A, that have got social ties with each other. For instance, first person has got social ties with second and third person. And they consider themselves as group A, who have the group person 3 is considering themselves as part of group C and group A. And each group also has got social ties with another group. Perhaps group A doesn't like group B and they want to avoid each other. Whereas group C likes group B and they want to be as close as possible together. Yes, that's just a quick example of possible relationships that exists within a crowd, that people consider themselves and others as part of a group, and they've got social links that define those relationships between groups, and they've got social ties that define the relationship within people of this group. You can just go onto Facebook and just see a lot of comments about us and them. It's quite common nowadays. So what I said during my PhD is, all right, if we've got the helping social force model, it works. Why not just add a new calculation to it by just saying, hey, why not add a force that attracts people towards other groups or tries to avoid other groups or other individuals that are not part of that group? And I've done that. Basically, I just said, yeah, let's take helping, let's make it better. And the result is actually quite simple, but it works. And I've got here the same simulation, just now I've got groups implemented. And you can see those groups quite nicely, like little groups of individuals trying to walk together, waiting for other people as part of the group. Like here, I've got a group of 3 that are always, group of 2 actually, that are always trying to walk together. Here, a larger group of individuals, as you can see, it changes the behavior quite a lot between individuals, basically crowd simulated on their own without the group aspect, and simulation as part of groups, that you've got more small groups of individuals walking next to each other. And that affects the results, the visual results of the simulation quite heavily. Even from top-down perspective, individuals are spread all around, whereas as groups, you can see little clusters of people walking next to each other, waiting for each other. It works quite nicely. But the big question is, which one is more realistic? Because at this point, I said, hey, it looks more realistic. But the question is it more realistic? Because often what you need to do, especially for serious crowd simulation, you need to ensure that the validation, that your simulation is as realistic as possible. For video games, for instance, it's enough to say, hey, the simulation looks and feels believable, which is enough for video games. But sometimes you want to make it as real as possible. So you need to ensure that the fidelity and realism of the simulation is as high as possible. And in research, anything that you create has to go at some point through a step of verification and validation, through getting some data, comparing some data, quantitative data, qualitative data. I'm not going to talk too much about it yet. I'm not going to talk about quantification, and validation in research at this point too much. I'm going to focus on crowds. So there's data about crowds. So you can get data like crowd density, flow rates, bottlenecks, individual velocity, etc., etc. And a typical set of data that you'll find a lot in crowd simulation papers or even crowd stuff is something called the fundamental diagram. The fundamental diagram is the relationship of a crowd between density and velocity. In other words, here you've got on this axis the velocity of a person in a crowd, and you've got here the density of a crowd per square meter. In other words, this chart shows that whenever there's individuals walking on their own in a non-crowded environment, that their speed of walking is quite high. But whenever individuals notice that they're walking in a crowded environment, automatically they walk slower. And the more crowded that square meter becomes, the slower individuals walk. It's just normal behavior. It's something that is ingrained in our psychology. We see an area that is crowded, we automatically slow down. And we can use that. That data has been actually validated quite a lot from real observations of crowd, then measured, etc., etc. It's not from a crowd simulation. It's standard stuff that you'll see everywhere. And I'm sure you can observe it around campus. Whenever it's crowded and busy, people walk slower. It's less crowded, people walk faster. And what we can do is use that data for verification and validation. By the way, earlier I had a question about cultures, and that curve about density and velocity, basically the fundamental diagram, is slightly different for different cultures. And a couple of papers actually looked at the crowd density and the fundamental diagram around the world, for Middle East, for Western cultures, for cultures in Southern Europe, for Asian cultures, and they got a lot of different results. But generally, the trend is still very similar. In a non-crowded environment, people walk fast. In a crowded environment, people walk slower. That's actually very fascinating stuff, because we can use that to verify and validate our model. And a simple approach to do this is get our crowd simulation, create a corridor, and then create thousands of individuals which are walking in a circle, in an endless circle, constantly, constantly, constantly. And then we measure the density, for instance, at a particular point. And if the density and the velocity follow a similar trend as the fundamental diagram, at that point you can say, yes, at least my crowd simulation can be validated to demonstrate realistic traits as seen in a real crowd. And if the crowd doesn't slow down in a crowded environment, something is wrong. And that's good. That's good. It's one step. However, there's more steps that you can use because we could use data from videos of crowds using AI. Because nowadays we've got so many imaging algorithms that are out there where you can just feed a video of a crowd and the video will just say, hey, there's this individual, there's this individual, there's this individual. It can identify individuals and track them. And there's another idea that people who are seen to be walking next to each other for a long amount of time can be perceived as part of a group. Makes sense. If you look at the high street and you observe individuals for a long time and you see 2 or 3 people walking really close next to each other for a long amount of time, you can just say, hey, those 2 people are family or friends. Makes sense because you wouldn't have 2 people who don't have any social ties with each other walking next to each other for a long amount of time. It's just actually stuff that has been validated and verified in crowd stuff. So what has Collins done in, that was an old paper in 2012, basically just looked at videos of crowds and applied the idea if they walk next to each other for a long amount of time, they can be seen as part of the same social group. And so for instance, here we've got person 1, 2, 3, and they're walking over a long amount of time next to each other. And using this chart, basically there's data collected from this video, it says, oh, these 3 people have got a high chance of being connected with each other. So in other words, if I look 1 and 2, I'm looking at 1 and 2. Yes, it's a white cell or yellowish cell. That means you've got a high chance of walking next to each other. Makes sense, they're walking in the same direction next to each other. For instance, we're taking person 9 and 12. Here we've got 12 and 9. There's a low chance that they are part of the same social group because, for instance, they may be walking in a completely different direction, or number 9 is just waiting there, whereas number 12 is just walking away. And that's great. By using that data, they can identify which one may be part of a social group. And what I did is, why not use that idea of measuring the connection between individuals of real people in on videos, take that algorithm, apply it on a crowd simulation. So I want to identify and create crowds that have good groups and automatically identify there are groups there and they behave like real groups. So what I did, I create my crowd simulation, again, with helping social force model with groups. I've got the corridor, but then on top of that, I apply the algorithm to identify groups and make sure that they follows a similar trend as a real crowd. So for instance, here I've got 8 individuals, and here I've got the trajectories showcase as dots. And as you can see, they all start together, but after a while, because they're part of groups, that they're trying to walk next to each other, perhaps avoid other groups, and avoid other individuals instantly. So for instance, here, in this, I've got 8 individuals. I've got 1 person as a group of 1, a group of 2, group of 3, and another group of 2. And by applying the algorithm, taken over from imaging and applied onto crowd simulation, I can identify those groups. And basically just says, for instance, let's check 5-3. Basically, I've got here, the brighter the color, the more likely that they group together. White box, most likely. The darker the color, the less probable a pair of individual is part of the same social group. So let's take 5 and 3. It's very, very bright color, so that means they're most likely part of the same social group. Makes sense, because if you observe them, they've been walking next to each other for a long amount of time. But if I take 1 and let's take 8, let's take 1 and 8, even though they walk closely next to each other at the start, they separated very, very quickly. So therefore, they can be seen not part of the same group. That is fantastic. It's little stuff that we applied from imaging, from robotics, from video analysis onto crowd simulation, which also takes stuff from computer science, from games computing and games technology, all merged together to ensure that the verification and validation of a simulated crowd is as realistic as possible. Which unfortunately now it's been what I've been talking for about 15 minutes, slowly head towards the conclusion. So what have I talked for the last 15 minutes? Well, I looked at crowd simulation in general. which is great. I looked at video games that are out there. I looked at quite a lot of things. I looked at the possibility to look at games technologies and use them into a complete different field, into a field of crowd simulation. And I'm basically saying, yeah, those two fields can benefit from each other because games technologies can provide computationally inexpensive methods to simulate large environments populated with large quantity of individual agents. Yeah, spatial databases work great in video games, work great for crowds, as I showed here. Stuff like games technologies, physics stuff, NVIDIA stuff works great to simulate physics. Let's use that. I also talked about pedestrian groups that have got an impact on the behavior of crowds. However, during a lot of crowd simulation, they have not been used a lot. Even in video games, you see individuals walking on their own, and you don't see groups of individuals that often, even though there's modern games that are slowly using groups more and more, which is fantastic. And also say they still need a lot of need to research verification and validation methods to reliably quantify group behavior information. That we're using a systematic method to say, yes, this crowd is as realistic as possible by X amount of value. And what I'm saying as well is using AI to create crowds supported by games technologies and computer vision techniques to ensure that the data is valid. Yeah, let's have a look a bit everywhere. Let's have a look at imaging. Perhaps there's already a solution there, but we just need to remanufacture it, change it, and adapt it to a different field, which is actually pretty common in research, just a matter of finding those right papers and adapting it. Anyway, guys, this is the end of my talk. I thank you very, very much for watching. If you've got any questions, feel free to send me an email. And that's it for me today. Thank you for watching. I'll see you around. Goodbye.